And that's the same as
All right, so recording is started. Welcome everybody back to our second installment of the GOCC for the spring of 2023. This week we are thrilled to have Jessica Stryker from North Dakota State University here to give us an expository talk. As a reminder, the GOCC has three guiding principles that we like to live by. The first is that we are all learning. The second is that everyone has something to contribute and no one has all the answers. So feel free to ask questions throughout. Again, everybody has something to contribute. So without further ado, please welcome Jessica Stryker to talk about alternating sign matrices and plane partitions.
All right, thank you very much. And thank you all for coming. I'm excited to tell you about two of my favorite combinatorial objects and lots of perspectives from which you can view them. This was the first mathematical topic I was really interested in graduate school, and it's kind of carried me all the way through my research career ever since. Almost everything that I've done has something at least tangentially related to one of these objects. So I'll tell you some of my favorite things about them. Be a lot of pictures, it'll be kind of fast. I do need to go and teach right after this, but I would be happy to correspond with people by email or whatever afterwards if you have any other questions that I don't get to. So here we go. Okay, got to make sure that it actually works. Okay, so what is an alternating sign matrix? Here's a picture and here's the definition. So it's a matrix with zeros, ones, and negative ones in it, such that the rows each sum to 1 and the columns each sum to 1. And then along any row or column, the entries will alternate in sign. The non-zero entries, there might be some zeros in between, but they'll alternate. And so if you sat down and played with this for a little bit, you'd realize that each row and each column has to start and end with a 1. And then there might be like some alternating -1s and 1s in between. So one question you could ask is, what does a really big alternating sign matrix look like? This is not a question I often ask, but there are, asymptotics is a really big thing and a lot of people do it. So here is a large one randomly generated by Sage. Alternating sign matrices are in Sage, so you can play with them. Here's an even bigger one. And you can kind of see that, that there's some structure here. Do you see something notable about this large ASM?
The corners are zeros.
Right. So like there's some random stuff happening in the middle, but the corners are all zeros. And so that's something called the limit shape of an object. It's like, what does it look like as it gets really big? So Colombo and Franco have studied the limit shape of large random alternating sign matrices in a series of papers starting in 2010. And they found it to be like almost a circle, but not quite a circle. It's like a piecewise linear, not piecewise linear, but piecewise circle. So it has like 4 circular pieces, but they're not like of a circle of that size. So anyway, here's the equation. And so outside of this circle-ish thing, there are fixed zeros in the corners, and then inside it's just like actually random. So they call that outside region the frozen region, and the inside region the temperate region, if you want to be connect to ice, which we will see a connection shortly. So anyway, you could also do something in enumerative combinatorics. So you could ask, how many of them are there? So it turns out there are 7 of these. If you fix the size of your matrix to be 3 by 3, you'll note all 6 permutations are there, and then there's a single extra one with a -1. And it turns out that there's actually really beautiful enumeration formula for alternating sign matrices. A long story associated with it, but you can, kind of look at the formula here and see that it's a product of ratios of factorials. These ratios of factorials are not actually always integers. So, but overall, the whole thing turns out to be an integer. And these numbers are really beautiful. They grow faster than n factorial, of course, so they're really big. And so there's a really nice story. Oh, hey, I have the book here outlined in this book by David Brosseau, which I carried around in my backpack for a long time in graduate school. And I still like it quite a lot. Proofs and confirmations, the story of the alternating sign matrix conjecture. So if you want to read more about the story, basically surrounding these 2 enumeration proofs by Zeilberger and Kupperberg in the late 90s, that's a great reference, along with the original papers. And then there's been some other work on proving this in other ways more recently. But here is my, my thesis problem, which is still open. Find a statistic on alternating sign matrices with generating function. This formula, when you put some Q's on it. So I tried a lot of things. It didn't work. I don't know, but it did seem like a good entry into this area. And in fact, at least it served the purpose of getting me interested, even if I couldn't solve that. Thankfully, I did solve a few other things. All right, so there's our first open problem, but now let's talk a little bit about bijections. Okay, so one reason alternating sign matrices are interesting is they're in bijection with lots of interesting things. In particular, they're in bijection with configurations of the square ice model of statistical physics. So you'll see some frozen water molecules there, and I'm told this is not how water molecules actually freeze, but just imagine H2O freezes like this. And it turns out that square ice does actually occur in not water, but in graphene. So this was a 2015 paper in the journal Nature. And you can kind of see there are molecules that sort of connect up at right angles like these ones do. Okay, the way the physicists usually look at this model is not with H's and O's because it's really hard to draw all of them, but with vertex configurations. So here's an n by n graph, a directed graph, where we have like some boundary edges of degree 1 around the outside, and then everything on the inside is of degree 4. And then we've specified our boundary conditions to be kind of interesting. So the arrows are all pointing out on the vertical on the top and the bottom, and they're all pointing in on the left and the right. And in the middle, they're one of these 6 configurations. So there are 4 configurations that correspond to zeros. And then the 1 looks like this, and the -1 looks like a rotation of that. Now, later in the talk, we're actually going to look at a new, what I'm calling a symmetrized 6-vertex model that will be useful to us when we want to try to look at this on sort of arbitrary graphs rather than just a fixed grid, because we don't, you need to have an up and down and a left and right to be able to distinguish between this 1 and the -1 and to be able to like set these boundary conditions accordingly. So basically what we're going to do later is something that's equivalent in this case to reversing all the vertical arrows. So I'll tell you more about that then, but this is the standard way to look at it. And it turns out alternating sign matrices are in bijection with lots of other things. And I'm not going to tell you about how all of these bijections work, but something, so I've already talked about the 6-vertex model. Shortly, we'll talk about fully packed loops and order ideals. And then later in the talk, bumpless pipe dreams, which have been of interest in Schubert calculus lately, will come up. And then there's also something called the monotone triangle, which is helpful for creating the poset that we'll look at. Okay, so I said that in each of the perspectives, we would start looking at some lurking dynamics. So here's the start of the dynamics. And that is, we're going to look at, I guess I should show you which object. We're going to look at these fully packed loops down here. And we're going to do sort of a local move on fully packed loops. Oh, I guess I should tell you what a fully packed, should I tell you what this is? Anyway, I don't have my, sometimes I have my presentation up and I can just like draw this fully packed loop on top of the alternating sign matrix, and then you know how it got there, but I am just looking at a regular PDF this time. But anyway, the way you can get this fully packed loop from this alternating sign matrix is you draw these boundary lines at like every other spot. And then the rule is in the inside, you turn whenever you hit a 0, one way or the other, left or right. There will only be one right choice. And then at each 1 or at each -1, you go straight. And so you can kind of see this straight line here on this fully packed loop corresponds with this 1, -1, 1. So anyway, it's really fun to like just draw a big alternating sign matrix and just try to draw your fully packed loop on it. Do everything that you have to do. And then, if you have a choice, just stop and don't, go to some other part of the matrix. I do this as like an outreach thing with high school students a lot. And anyway, it's really fun. So if you want to just do that for the rest of the talk, feel free. All right. So here's what we're going to do with fully packed loops. We're going to look for spots that have 2 vertical lines or 2 horizontal lines, and then just do this move, transition this from, go between the vertical to the horizontal. And so we're going to look at our fully packed loop, and we're going to do this on all the even squares. So like color your fully packed loop like a chessboard and just look at the even ones. We'll call this parity even. This is the only one that has that just vertical configuration or horizontal, and so we'll flip that. And then now we'll go back and look at all the odd squares and do the same thing. Find the ones that are parallel and flip them. And now we have a new fully packed loop. And as it turns out, if you label your vertices around the boundary, what's happened is like some stuff in the middle, especially for a bigger fully packed loop, you can't really say exactly what's going to go on in the middle, but you can say that, well, if 2 was connected to 5, and then I did this action, which is called gyration, composing all of these local moves, now I'm going to have the edge from 1 to 4. So it's going to rotate this non-crossing matching associated with your fully packed loop of like what is connected to what. So that's something that was proved by Wieland, I guess 23 years ago, and he was an undergraduate. So basically that gyration on this fully packed loop will rotate that associated link pattern. And then more recently with Dilks and Pajenik, we gave a name to this, and we saw this phenomenon arising in other situations where you have some sort of complicated action on some objects, but it projects to something that we understand, that we know the order of, so something nice like a rotation. And so we said that gyration exhibits resonance with frequency 2n because 2n is what the thing on the bottom gets rotated by, even if gyration up here can have, you know, an unpredictable orbit sizes and order.
I've got a quick question.
Yes.
So it sounds like it takes 2n of these. Well, you have some periodicity to your rotations of your non-crossing arc diagrams or non-crossing diagrams, but is it do you actually return to your starting state with the fully packed loops?
No.
Okay.
I mean, not in general, every once in a while maybe, but no, I mean, those
Right,
orbits,
there's a finite number of them, so eventually, given enough time, you will, but
yes, you will eventually, but not in the first 2n. Maybe,
yeah.
no, you have to go around a few times. So, yep, thanks. All right, so now let's look at another object in bijection with alternating sign matrices. I didn't really tell you what these are, but these are basically like strict Gelfand-Setlin patterns with some inequalities on them. So these are monotone triangles. So here are the 7. And if you take these objects and you just put them in order the way that you would put them in order if I just threw the objects at you, which is by component-wise comparison. I've done this with high school students again, and this is how everybody puts it together in this way. So this is the partial order on alternating sign matrices. And it has a neat property observed by Lescaut and Schutzenberger that if you just look at the ones that correspond to permutation matrices, so it's everything actually except this one in the middle, you get the strong Bruchau order on the symmetric group. So that's kind of neat. And in fact, it's the smallest lattice that contains the strong Bruchau order as a subposet. So it's called the McNeil completion of the strong Bruchau order. So anyway, that's kind of a neat fact that I won't really build on at all, but it connects to permutation posets if you care about those. All right, so but here's the way I want to look at it. So in fact, this alternating sign matrix poset is a distributive lattice, which means it's the poset of order ideals by component-wise comparison. Anyway, there's the fundamental theorem of finite distributive lattices, but basically a distributive lattice is like really, really nice. And here's what you can do. You can look at it as the set of order ideals of a poset that looks like this. And here I'm just trying to show you how to construct this poset. So this poset is actually a tetrahedron. And n by n alternating sign matrices are in bijection with order ideals in this poset. Now you might recognize those layers as things whose order ideals are given by the are counted by the Catalan numbers and in bijection with thick paths. So one thing I like to think of is alternating sign matrices are really like a bunch of layers of Catalan objects kind of stacked on top of each other. All right, and so now I want to connect this back to the fully packed loops, and I'll just show you sort of a series of pictures here. So take your fully packed loop and kind of put it into the plane, like squash it down a little bit. So let's see, pay no attention to the numbers. That's a height function matrix, another thing that they're in bijection with. But here I'm going to draw this. Here's this tetrahedral poset, or this tetrahedron of these layers. So there's 4 of these Catalan type layers kind of stacked on each other. So here is the order ideal that corresponds with this fully packed loop through a correspondence that I won't quite tell you about, but I could give you a reference to, well, one of my papers where this picture was. But basically, you have these red lines going from each of these squares that basically tells you how many things in that red line should be in your order ideal. So there is actually a nice way to match this up. And even better, if you do gyration on the fully packed loop, it has a nice effect on the order ideal. So I can describe to you exactly what that effect is on the order ideal. Here's what it is. So what you do is you look at all of the even ranks of this poset. So this poset, the bottom of this poset is actually these 4 elements down here. You kind of have to look at it sideways, but basically you look at every other rank, toggle all of those, meaning you just kind of take them in or out of the order ideal if what remains is still closed downward, if it's an order ideal. So you toggle all of those, and then you toggle all the rest of them. So it's just like the even and odd in the definition of gyration on the fully packed loops. And this was, this was the first theorem I ever, in the first paper I wrote that had something to do with toggling, and then there's another whole story with the toggle group and row motion and things like that. But this was really my entry point, is that, hey, this does something really cool on alternating sign matrices. So there's also another action on any poset that you can look at by just toggling everything from top to bottom. So on this poset, top to bottom looks like that. We call that row motion. But what we can get from this, from relating it back to gyration, is that row motion on the alternating sign matrix poset is going to have the same orbit structure as gyration. So it's going to, in fact, exhibit this resonance phenomenon with that underlying rotation. So anyway, that's kind of neat. So that was a lot of stuff with a lot of pictures about alternating sign matrices. But the title of this talk was a dynamic duo. So we'll switch over here for a moment and talk about plane partitions. And then we'll do some of the similar, sort of a similar sequence of things as what we just did here, looking at asymptotics and enumeration and bijections. But first, a definition. So a plane partition is a bunch of cubes pushed into a corner. I happen to have like a really big one here that a student 3D printed for me once. So anyway, there's cubes in a corner, and it's pretty cool. He said he had to try 3D printing it like 6 times. And so here's one that didn't work out so well. It had to be glued. But anyway, so that's, or you can look at my picture right here on the screen. So stacks of cubes in a corner, and it's a classical result of Percy-McMahon that the number of plane partitions inside an A by B by C box is given by this lovely product formula. You just take the product over all the possible boxes in your A by B by C box of its position, I plus j plus k minus 1 divided by I plus j plus k minus 2. So super pretty formula, lots of stuff that's fun to look at with plane partitions. One thing that's fun to look at is symmetry classes. So you can look at plane partitions. So this one here kind of didn't have any symmetries, but you can imagine if it was, say, symmetric, reflectionally across the middle, or perhaps rotationally, by rotating 120 degrees to basically change each of these different directions of boxes into each other. So there's cyclic symmetry, there's reflection symmetry, totally symmetric if both of those hold. And then there's a property called self-complementary, which I'll use my smaller 3D printed versions here to show you. Plane partition is self-complementary if, when you have 2 of them, they can go together to make a whole cube. Okay, so much easier to show you than to try to describe it like I did for many years before that. So here's a picture of a totally symmetric self-complementary plane partition. I don't think it's the one I showed you. Ooh, which color is that? Oh, that's this. Ooh, I think it's this red one. So anyway, so you take 2 of those, and if you put them together, they're self-complementary. And then there's something else called transpose complementary also. So it turns out like all the different combinations of these symmetries are, let's see. Oh yeah, okay. All these different combinations of these symmetries have nice product formulas, and it took some time for all of them to be proved, but they're all proved now. I started talking about enumeration first. Okay, so first, asymptotics. What does a large, random, totally symmetric self-complementary plane partition look like? Well, there's one of them generated by Sage in a ticket that still isn't put into the main distribution of Sage, but like we have code to generate totally symmetric self-complementary plane partitions. So if you're interested and you're a Sage person, you could try to finish that ticket. But anyway, there's not that much left to do. But yeah, now I'm really happy because that we can generate these large random things. And I don't know exactly what the limit shape is, but I think Ayer and Sheeta do. I just couldn't I need to email Arvind Ayer and ask what it is, because I couldn't figure out. There were a lot of integrals in that paper. It looked very complicated. They proved some other stuff too. But I think somebody knows what the limit shape of these guys is. And my guess is it's not the same as for alternating sign matrices, because there was that like 4-fold symmetry there. And here, this is probably more of a 3 or a 6-fold symmetry. So sometimes people say that maybe, I don't know. Anyway, we'll see. But that's what it looks like. And we can generate them in Sage, and it's really fun. And you can kind of see it's sort of similar, though. It's like you have some random stuff in a circle and then some stuff that's fixed outside of the circle. So that's what it looks like. All right, now we can talk about enumeration. So if you fix the size of your bounding box, it turns out you have 7 TSSCPPs inside a 6x6x6 box, which is a number we've seen before. And it turns out that the same product formula counts the number of totally symmetric self-complementary plane partitions inside this bounding box. That was proved by Andrews a little bit before, actually, the alternating sign matrix enumeration was proved a couple of years beforehand. So this has been an open problem for nearly 40 years, because it was guessed that these two should correspond before these things were proved. But one would want to like take one of these totally symmetric self-complementary plane partitions and turn them into an alternating sign matrix in an invertible way, right? We would like to have a meaningful bijection between these two sets of objects. But a lot of people have worked on this and nobody's been able to do it. We do have some sub-bijections though, which I will describe in a few minutes. But also, there are some known bijections. So if you take a totally symmetric self-complementary plane partition, well, the first thing that you might note is there's like a lot of symmetries. I'll take my big one here, right? You don't need all of this information to be able to tell you which one you have, because you know that if you rotate it like this, it needs to come back to the same thing, right? Or if you do the symmetric, if you do it symmetric across the axis. So like basically all of those symmetries need to be satisfied, and the self-complementary condition. There's a lot of conditions. So really all you need is like 1/12 of this hexagon, and then you can reconstruct the rest. So this 1/12 of the hexagon is called the fundamental domain. So let's look at that information. So you can organize this information either as by counting how many numbers are in each stack, or by looking at these paths that trace out each level. And so the numbers in the stack can turn into something called a Magog triangle, which I worked really hard in my thesis to try to make look as similar to those monotone triangles from the ASM world as possible, but they're a little different, and I don't know how to morph one of them into another bijectively. But also these lattice paths have been very interesting. It turns out that they are non-intersecting lattice paths that look sort of like this. You'll notice they have 2 different kinds of steps corresponding to the 2 different kinds of steps these paths can take. And then I'll explain this order ideal thing as well. If you take these, sorry, I'm scrolling too much. If you take these Magog triangles and you order them the way that you would if somebody just gave them to you by component-wise comparison, you get something that looks like that, which doesn't look the same as for alternating sign matrices. But if you look at the structure of these as a distributive lattice, it turns out that you take these same Catalan layers and you layer them on top of each other in a different way. It's right justified and underneath, right? So it's not a tetrahedron, it's some sort of a wacky other kind of structure. But totally symmetric self-complementary plane partitions inside a 2n by 2n by 2n box are in bijection with order ideals in this poset. So you kind of stare at those posets and you can try to morph order ideals from one into the other. And there's, I don't know, there's just no way to do it, or at least I didn't see how to do it. But I do think it's neat that they're both like, you can think of them as, a bunch of dict paths or Catalan objects that interact in like different ways and turn out to have the same number of each of them, of the order ideals of these posets. Okay, but what can we do as far as bijections are concerned? So a good place to start when you're trying to do anything with alternating sign matrices is with permutation matrices, because we understand those very well. So as it turns out, I know you can figure out which ones of these TSSCPPs correspond to permutation matrices. So here's one. And so like you look over here and you know what's special about this, right? There's no negative ones. And you look over here and you ask yourself, well, what's special about this? Well, as it turns out, these paths kind of have a very interesting structure. Namely, if you look at it the right way, if it starts, so all of these black steps here, if you kind of zoom in, I guess I could zoom in, but all of the black steps in each of these columns here are left justified. So you can see the little hand I have here, right? Okay, so notice in this column right here, you have a black box, and a gray box underneath those paths, and all the black boxes need to be justified to the top. So here's another one, black, gray, 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 gray. Okay, so there are no grays followed by blacks, which means there are no configurations of a gray rhombus followed by a black rhombus as you move down these columns. So that's what corresponds to having no negative ones. And then here's how the bijection goes. It's pretty nice. So you just take these paths. I like to turn them into what I call Boolean triangles because zeros and ones made a little bit more sense than these two like weird diagonal and up steps, but the up steps are ones and the diagonal steps are zeros. And then there's some condition on these triangles that says it's a Boolean triangle, even not in the permutation case. We have like an inequality condition that corresponds to these boxes not falling, out like gravity working correctly in this fundamental domain. So you turn it into a Boolean triangle, and then you can turn it into this monotone triangle, which was one of the objects in bijection with alternating sign matrices by like a simple rule that just says all the zeros, they need to be equal to the number to their right, and all the ones need to be equal to the number to their left. And that ends up turning into a permutation matrix, basically just by reading off what the new number in each row is, 4, 6, 3, 5, 1, 2, corresponds to this permutation matrix. All right, so that is a super easy, nice bijection. And the question is, can we extend this bijection beyond permutations? And the answer for a long time was no. Like I knew about this bijection. It just took a while to write up the whole paper because I added some stuff to it. So I mean, I've known about this bijection for like 10 years. And I had no idea how to extend it beyond permutations. But recently, a new tool appeared and we were able to extend it not to the whole bijection, but to a significant subset. And the new tool was, well, basically bumpless pipe dreams, which relate to Schubert calculus and a bijection of Daoji Wang and Yibo Gao between these two kinds of objects. So Schubert polynomials are interesting polynomials. They're sort of like souped up Schur polynomials. So if you like Schur functions, these are, sort of a lifted version of those, but associate to each permutation some polynomial. And there are rules for writing down this polynomial. Send to Zoom, don't. Hello, can you guys hear me?
Yes, we
Yes.
can still hear you.
Yep.
Oh, great. I got some weird Zoom crash thing. Okay, so can you, all right, so both of these objects can be used as a combinatorial expansion of Schubert polynomials. And so these bumpless pipe dreams are newer, but if you look at these, and then these objects, so these objects, they're associated to a permutation just by writing across the top of this pipe dream or across the bottom of this bumpless pipe dream, the numbers 1 through n, and then just see where the pipes go on the other side. As long as they're reduced, that rule works. And so then you just write down all the possible pipe dreams or bumpless pipe dreams for a permutation, and then write down a monomial in a certain way. This monomial asks, where are the tiles in this pipe dream? What rows are they in? So there's 2 in row 1, 1 in row 2, and 1 in row 3. And then, or if you're going to go look at these bumpless pipe dreams, it asks about the blank tiles. So there's 2, 1, 1. So I'm not going to give you the precise definitions of these things, but they're objects that look like this. These kinds of tiles put on these kinds of grids. All right, so the new tool was this bijection of Gao and Wang between pipe dreams and bumpless pipe dreams. And I heard, so I met Daoji in an ISERM seminar in the pandemic. So I wasn't going to go to ISEM for this conference, but then I saw that there was some stuff related to bumpless pipe dreams. So I showed up for an online talk and I talked to her a little bit. And this was before she had discovered this, she and Yibo had discovered this bijection. And somebody in that talk was talking about, you know, pipe dreams and bumpless pipe dreams. And oh, it would be like really hard to figure out a bijection between those objects. And I was like, hey, a really hard bijection that like relates to things that I know about. Because as it turns out, bumpless pipe dreams are actually alternating sign matrices in disguise. So then when she and Yibo figured out this bijection, I was like, well, surely this has something to do with the problem that I care about. So first I'll tell you about their bijection, and then I'll tell you how it relates to alternating sign matrices and plane partitions. So their bijection is really nice. You can start on the bumpless pipe dreams side, and basically you're going to try to change this thing into the identity bumpless pipe dream by getting rid of these blank tiles. And then you're going to record over on the right, basically which two pipes uncrossed to give you, to get rid of that blank tile. So here, pipes 3 and 4 uncrossed right here. And so this goes in the first row because the blank tile came from the first row, and it goes in the third diagonal because pipes 3 and 4 uncrossed. And then the same thing happens. You just kind of like successively remove these things using these droop moves and then record in the right row and diagonal where they go. So there, pipes 5 and 6 uncrossed. So you're in this diagonal 5. And then finally, you keep doing this until you get to basically the identity bumpless pipe dream. So this is the bumpless pipe dream that corresponds to the permutation 1, 2, 3, 4, 5, 6. And now we have something with these cross tiles. And if we just fill in all of the rest with the only other possible tile for what a pipe dream is, you get something for that permutation with the crosses in the correct rows so that that weight for the Schubert polynomial is preserved. Okay, so what does this have to do with our problem? Well, bumpless pipe dreams are alternating sign matrices. Oh, I should have shown you how that, I'll show you on a later slide how they correspond. And then our new perspective is actually, you know, these triangles with 0s and 1s that came from the paths and the TSSCPP, well, you can make them look a little bit more like a pipe dream by putting the triangle in the correct orientation. And then now we're going to turn our 1s into crosses and our 0s into the bump tiles. So TSSCPP are actually pipe dreams also. Now notice there's like a little bit of reduced and non-reduced in both of these spots. So that's like why we're not going to be able to get a full bijection, because the result of, if I go out, oh yeah, there we go. This result is for reduced pipe dreams and reduced bumpless pipe dreams. But still we can get a long ways with that. So here's our theorem, is that we have an injection from reduced TSSCPP whose pipe dream ends up being reduced, to alternating sign matrices whose bumpless pipe dream is reduced. So you can always map from the TSSCPP to the ASM as long as the TSSCPP was reduced to begin with, and sometimes they're not. But if your permutation avoids 1, 4, 3, 2, then this is in fact a bijection, because all of the, well, I'll show you about that proof in just a second. But first I got
we lost her. Okay. See if she comes back.
Yep, we'll see if Jessica can return. Apparently the Zoom problem's actually finally caught up to her.
Right.
Okay, thanks. All right, so so here's the main result, that we have a map between TSSCPP and alternating sign matrices in the case that the corresponding pipe dream and the corresponding bumpless pipe dream correspond to a permutation that avoids 1, 4, 3, 2. So I think I was just about to ask you what correspondence you might see between these two things, but the correspondence is really simple. So like these kind of tiles are 1s, these kind of J tiles are -1s, and then everything else is a 0. So there's actually like 4 different kinds of zeros, just like with the 6 vertex model. So anyway, this correspondence is easy. This correspondence is pretty easy. This correspondence was that algorithmic thing I showed you from Gao and Wang. All right, so, and then here's sort of the proof. So we characterized the TSSCPP using something we're calling a pseudo-Yamanouchi property, which has something to do with these paths, not disobeying gravity. And as it turns out, simple slides, which are basically moving across diagonally one space, preserve the pseudo-Yamanouchi property. Then if your permutation avoids 1, 4, 3, 2 by a theorem of Gao, any 2 reduced pipe dreams are connected by these simple slides. So that tells, and the pipe dream with all the crosses left justified, called the bottom pipe dream, is pseudo-Yamanouchi. So that means all of the other TSSCPP are also pseudo, or all of the other pipe dreams you can get to by those simple slides are also pseudo-Yamanouchi. So that means we have a bijection between TSSCPP and ASM in this case. All right, so there are questions, will this lead to, will we be able to push it farther? There are some obstacles to pushing it farther, but that's something that I'm really interested to look at next is, can we use this perspective to either find a bigger bijection or show that a bigger bijection isn't going to work, which that's a little harder to state, but it might be possible, you never know. All right, so any questions? All right. Okay, so the next section, I have 2 more things basically I want to show you. One is sort of a polytope way of looking at things, which I will basically zoom through. The punchline is you can make polytopes out of alternating sign matrices and they're cool. So here's a polytope. You take a bunch of points and you look at their convex hull. So all the space in between them, you consider it as a geometric object. I'll forget that for a minute. So here is the alternating sign matrix polytope. You just treat each of the alternating sign matrices as points in 9-dimensional space, and you add them up with these coefficients in front that have to sum to 1 and are greater than or equal to 0. And as it turns out, since the rows and columns sum to 1, this polytope isn't actually 9-dimensional. It's only 4-dimensional because you actually don't need the last row and column. Those are determined. So we can make polytopes out of this and out of lots of other things. So permutation matrices, and then like rectangular permutation matrices and rectangular alternating sign matrices, and something called, sign matrices, which are in bijection with Tableau. So anyway, all of these is like a different paper, but basically we can prove inequality descriptions. So there's a classical proof of Birkhoff and von Neumann for permutation matrices that you can have a nice inequality description for that polytope. So, and there's a theorem of Mirsky about these rectangular cases. And then this was the very first paper I ever wrote. And it was also at the same time studied by Behrend and Knight. And we found this inequality description that's very nice for alternating sign matrix polytope. And this is a point inside that polytope. So sometimes you can have negative entries, but the partial sums in rows and columns need to be non-negative. And then more recently with my grad student Dylan Hoyer, we came up with some similar theorems for this rectangular alternating sign matrix case. And here's sort of you shouldn't really read this necessarily, but we can figure out the dimension and the vertices and the number of facets for like all of these different polytopes. And so those are fun enumeration problems that relate to geometry. But the lurking dynamics that I'd like to show you in the polytope perspective is answering the question, how do you know if 2 alternating sign matrices are have an edge between them, like an actual edge in the polytope? And so the way you figure that out is you look at these 6 vertex configurations and you see where do they differ. So here's where this one differs from that one, is that they just differ in this one one circuit, so like one cycle here. So if you just smash the two vertex configurations on top of each other and there's a cycle in between, that means these guys are actually an edge in your alternating sign matrix polytope. And this cycle, if you just change the edges like one by one on each of these spots, this would be the same as that local move on the gyration, or as a toggle in that alternating sign matrix poset. So this dynamics has a geometric meaning. All right, so I do have just a little bit of time to tell you about basically maybe why Stefan invited me to come give this talk. So alternating sign matrices do end up showing up more recently in representation theory. So if you know something about spec modules or web bases or cluster algebras or something, this slide might mean something to you. But basically there's an algebraic world in which we're trying to find combinatorial gadgets that help us explain algebraic things or give us a basis for different spaces. So I'll show you a few examples. So for example, there's a spec module. So you can look at this shape D, so like two rows, D of length D, and one combinatorial basis for the space is all the standard Young tableau. And a different combinatorial basis, which is better, in my opinion, is that of non-crossing matchings, because you can rotate a non-crossing matching and get back to where, or get another non-crossing matching. Whereas over here, you have to do, it turns out you have to do promotion on these tableau, but actually just rotating the numbers isn't going to work. So anyway, so either of these things give us a basis for this spec module. And then what is promotion? So promotion is actually going to be important. And this is kind of a fun game where you delete the one and then you just slide the smaller entry over into the blank space, and you keep doing that until the blank space ends up at the outside. And then you fill it with the next number higher and subtract one. And there you get another tableau, right? Numbers in boxes with the rules that you have to be strictly increasing in rows and columns, and you use each number once. Okay, so there are some situations in which, so the spec module always has a basis in terms of the standard Young tableau, but it doesn't always have great properties. And sometimes for special shapes, it has a different drawing that you can rotate that is like the web basis for that shape. So I'll show you a few shapes that have such a nice basis. So two column tableau have another nice basis. This looks a lot more complicated than non-crossing matchings, even though you could just like turn it this way. So this is a recent paper of Chris Fraser. Fun pictures. Here's another recent set of papers by these authors, one of which, my paper is with Petrius and Pagenik, and then Brendan Rhodes and Kim also looked at this from a different perspective. But basically, if we take shapes like this, we can turn them into non-crossing partitions. And then those, we end up getting like polynomial bases for these spaces from the picture that behave nicely. Okay, so then here's another one. So back to the 2-row tableau, we can also do this with 3-row tableau. So you can turn this tableau into this picture that rotates, and it's also rotates and matches up with promotion and gives you a basis for the spec module. But notice this result was really a result of Cooperberg in 1996. And at that time, and ever since, people have really been wondering, can we do this for 4-row tableau and beyond? Because one nice thing is that promotion on rectangular tableau is always the order, the number of boxes. And there kind of isn't a nice pictorial explanation for that beyond the 3-row case. So we'd really love to see something that rotates when you do promotion on a rectangular tableau, and then it would end up having this like representation theoretic significance. So this was extended to things that don't look like rectangles, to things called generalized oscillating tableau. And this was, something that was also in the Cooperberg basis. So notice this guy still has 3 rows. I won't exactly explain what's going on here, but you can turn this into this picture that does rotate with an analog of promotion over here. So we can do 3-row rectangles, we can do 3-row weird oscillating tableau shapes, and now we can do 4-row shapes. And so this is joint work with Gates, Pachenik, Fannerer, and Swanson. And we've found diagrams that you can rotate, and that gives you promotion over here. So there's a bijection between these tableau, and diagrams that we're calling hourglass playbit graphs. So notice there are vertices of 2 different colors, and there are these little hourglass edges in some spots. But the weird thing is that it's not a bijection between tableau and one diagram. It's a bijection between a tableau and an equivalence class of diagrams that relate to each other using certain moves. So we have actually 2 kinds of moves. So I'm showing you one here. So this tableau in particular corresponds to these two hourglass playbit graphs. So in general, so here are the different moves we can do. So the one that I was showing you was something sort of like this second move here, where we're taking hourglasses and turning them into not hourglasses. So we could actually have like hourglasses of, any number of them around here, and they'll just swap out whether they're there or not. And then we also have this kind of a move that will take a hexagon and just change the hourglasses to be in the other spots around it. So basically, if we look at all of these kinds of graphs that turn out to be like 4-valent with these hourglass edges allowed, with just all black edges around the boundary, these are these equivalence classes modulo these moves are going to be a web basis for the spec module that does rotate with promotion. All right, and now what does this have to do with alternating sign matrices and plane partitions? I told you we would come up with a symmetrized 6-vertex model. So I've done a little bijection here. I've taken all of these hourglass edges and kind of smushed them, and I've put orientations on the edges. And so there's a bijection between these hourglass playbit graphs and what we're calling symmetrized 6-vertex configurations modulo these moves. So both perspectives end up being really helpful in this super complicated proof. And there's a lot of underlying combinatorics and algebra and crystal theory that are related to this statement here. But I want to concentrate on where do alternating sign matrices and plane partitions show up. So here is a tableau, a 4-row tableau. We're always talking about 4 rows, but 3 columns. And it turns out that in its equivalence class, there are 7 things. And these 7 things, well, you can sort of look at these moves, and it turns out these moves are the same as like walking around on the alternating sign matrix polytope, or that move on the fully packed loop. These 7 things are in fact in bijection with our 7 3x3 alternating sign matrices. So alternating sign matrices pop up as equivalence classes of corresponding to tableau in our spec module. And not only that, the talk was about a dynamic duo. So it turns out this thing on the right here, this is a plane partition, if you look at it the right way, if you think about it as dimer covers in the hexagonal lattice, for example. And its equivalence class is all plane partitions in I think a 3x3x4 box or something. And it corresponds to what we're calling fluctuating tableau or generalized oscillating tableau on 4 rows. So this is like a blank 3rd row right here. So these pop up in our construction as well. So it turns out that our graphs basically have alternating sign matrix regions, equivalence classes, and plane partition regions or equivalence classes. So anyway, there's our group. This person over here, very well. And there's our theorem that we actually end up getting a web basis for all of SL4. So with that, I'll stop there. Thank you very much.
Let's thank Jessica. And if she has time for a quick question, I know you have somewhere to be.
Yeah, I just need to run downstairs by noon, so I could, a couple of questions would be fine. Yeah.
I guess I have one hopefully quick question. When you were first talking about gyration for the fully packed loops, you're saying that it represented toggling in the poset representation, but both of these are 2-step processes where, like, with gyration you flip and then you flip, and then with toggling you do this. So is there a bijection between those processes, or do you need to combine the 2 before they actually sync up with each other?
Oh, no. So the gyration, when you toggle the even and odd ranks of the poset, each of those match up exactly with toggling stuff toggling the even and odd squares. It's just, you've taken this tetrahedron and kind of smashed it into 2 dimensions. But if you do it along those red lines from the picture, then yes, it does work out exactly.
Okay, it's just by alternating between them, you actually get the nice rotation.
Yeah.
Okay.
Yeah.
Thank you.
Other questions? If not, let's thank Jessica one more time.
I have a quick, Jessica, I have a quick question.
Yes.
This is a very impressive subject. Do you have, or have you written or otherwise point us to like a survey of all the variations of models of alternating sign matrices that you outlined, the first half of your talk?
Sure. I mean, there are, so for all of those different bijections that are known between the various, there's this paper of Jim Propp called The Many Faces of Alternating Sign Matrices. So that'll have all of those bijections in there, but not the order ideal thing. That was in a paper of mine called something about Razumov-Stroganov conjecture, but anyway, so I guess I don't have that here.
Yeah, let's go ahead and thank you again, Jessica. We'll call it here for today.
That sounds good. Thank you.
Thank you so much, everybody, and we will hopefully see you next week.